Hello, today I will speak about machine learning in the context of its use for ultra-fast non-linear fiber photonics. So before starting, I will first like to thank the different coding edge students I had a great pleasure to work with. So I will show some of their contributions that are great. This tutorial, this is devoted to newcomers in the field of machine learning, so to people that never had the opportunity to delve into it. I will start with a few words on artificial intelligence and recall the principle of the evolution of a pulse when it is in presence of nonlinearity. And after this, I will show four different sections with illustration of different uses of machine learning approaches. And I have put in the slide different reference so that if you want to go into more details of the different technique, you will know the article where you can find some more information. I think this is impossible not to have heard of machine learning. This can be funny, this can be sometimes frightening, but this is now here. And usually people, when they are thinking in terms of artificial intelligence, they think that it is restricting to huge companies that can have some tremendous facilities in terms of computing power. However, it is absolutely not the case, and you can play with machine learning on desktop or laptop computer. What is nice with machine learning, this is that you can easily find plethora of resources. It can be mocks or very well written books or review articles. And there are also a large amount of codes that are open source, and this is really high level codes. So you can use them. It will be a level of performance that is extremely interesting. So you do not have to rewrite every time you run code. Usually people, when thinking in machine learning, they believe that you absolutely need to do everything in Python. It is not mandatory. If you are not familiar with Python, it is absolutely okay to work with MATLAB or with Julia. And machine learning is not restricting to expert in computing science. It is also highly interested for people doing research in physics and in photonics, and people from physics can contribute to the field of machine learning, as it has been shown by the Nobel Prize last year in physics. Now, behind the word of machine learning, there is not a single approach. There are plenty of very different approaches. It is impossible to cover them in less than an hour, so I have only selected a few that I think are the simplest one, and I will try to convince you that even if those techniques are simple, they are already extremely powerful. And what is nice when it comes when merging the field of photonics and machine learning, this is that you have a win-win interaction. Photonics can be beneficial for machine learning by providing a new physical support. And in the other way, machine learning can help the design on new photonics components, and it can also help to have a better treatment of an optical signal. The topic of this talk, this is not photonics for machine learning, but here are some examples. You see that there are many different possibilities. It can be some diffractive optics. It can be 3D printed photonic structures. It can be spiking lasers, multimode fibers, interferometers, or the use of a frequency comb. If you are interested in that topic, that is really exciting. Here are a few review articles that will convince you of all the advantages of photonics in terms of speeds and energy efficiency, in terms of reduced heat, of high bandwidth, or massive parallelism. Now, machine learning for photonics. Machine learning has been used, for example, for signal treatment in optical telecommunication, in imaging to improve the quality of the images. It has also found very interesting application in terms of component design, where it has enabled the development of a new generation of highly efficient devices. So, once again, a few references. Today, my main focus will be the field of ultrafast optics, and more specifically, when it comes with the propagation in an optical waveguide in presence of nonlinearity. And in that case, your pulse will experience the consequences of dispersion that will not affect its optical spectrum, but it will change its temporal intensity profile. And the Kerr nonlinearity, it is a nonlinear effect that will change its spectrum. When you take both effects into account, you have the nonlinear Schrödinger equation. Usually, you can also easily include gain and losses, and there is a way to numerically solve this equation, which is the use of the Splitter-Fourier algorithm. This is the algorithm that has become the standard in the community and which is pretty efficient. But before going into artificial intelligence and machine learning, when you have an equation, you see here, only taking the parameters of the fiber, you already have 4 variables. And if you add the description of your input pulse property, you add another 4 parameters. It is interesting just to do some math to check that there are no scaling parameters in the equation that you consider. For the NLSC, this is the case, and it enables you to find normalized variable that will diminish the number of parameters you need to handle, and it will make everything easier. And it will enable us also to better visualize the result in the space of these reduced parameters. So let us now start with machine learning. And the first thing I would like to discuss, this is machine learning for prediction of the output of the system. The main idea, this is to mimic what happens in our brain, where you have some biological neurons. So you will build an artificial neuron, and how does it work? You have some input parameters, and you have an output, and you want to link the two, and you will do that by using a weighted sum of your input with some bias. So here, this is a linear combination, and you see the weight and bias are the parameter that will define your neuron. So you will have to find them. This weighted sum, it will go through an activation function, which is a nonlinear function. I have put here 2 examples of such activation function. And at the end, you obtain your output. And you can already play with this artificial neuron on very simple configuration. Now, if you want to deal with some more complex problems, you need to increase your number of neurons, and you have to connect them, organize them. There are plenty of different architectures that could be suitable. Here, I have chosen the simplest one, where you put your different neurons on different layers, and all the neurons are connected to the previous layer and to the next layer. So this architecture is known as a fully connected neural network, and it is also feed forward because you see all the connections go in the same direction towards the output layer. So now you have an artificial neural networks, whatever its internal architecture is, it will link input to output. And the goal, this is to mimic a physical system. What you want, this is a digital twin of your physical system. And it is possible to have such a feature with an artificial neural network because a neural network is an universal interpolator. So if you have a response that links the output to the input in your physical system, if you have enough neuron in your neural network, then the neural network will be able to interpolate this response. But before everything works, there is an important stage, which is the training. And the training requires data. So you need to have pairs of input, of output, and you need a large data set. The more data you have, the better will be your accuracy. This data, they may come from experiment, or they can also be synthetic data that you will have generate using numerics. For example, you have solved the nonlinear Schrödinger equation using the step Fourier method. How does this training happen? So you start with your data. You usually have to go through a small normalization stage, and then you will take one part of your data, a large part of those initial data, to train your network. What does it mean? The training, this is the stage where you will find the different weight and bias for each neuron. So it can be quite a lot of parameters to find. Imagine you have 100 neurons that are involved. It can lead to perhaps 10,000 parameters to find. But don't worry, because there are some optimization algorithms that works extremely well. So they have been the key for the development of machine learning in the 80s. And for example, you have the backpropagation algorithm or stochastic gradient descent that will be able to provide you the best combination on weight and bias for your system. You do not have to code them. They are already available in all the packages that deal with artificial intelligence. One thing that you will have to define, sometimes in a quite empirical way, these are the hyperparameters, such as the number of layers that you will use, the number of neurons on each layer, your learning rate, the details of your loss function, and so on. So here you have to make some tests to find something that works pretty well. And once you are happy with your training, then you will validate the behavior of your neural network with some part of your initial data that you have not used for the initial training. So here it will confirm you that your neural network is able to make prediction of unknown data. And if the test is okay, you will then be able to use your artificial neural network as a black box. You do not have to care anymore on the initial set of data you have used, and you do not have to know the fine details of what you have in your black box. So you see here, this is the main idea of this use of neural network. I will try to convince you that it works even if you consider simple structures. So the goal here in this work, it was that we defined the parameters of the propagation in terms of normalized unit. So those are the parameters of the fiber and the input pulse. And we have built a neural network that is aimed at predicting the temporal and spectral intensity profile. So what we can see first that upon propagation, the input pulse experience some large changes both in the temporal and spectral domain. And we see that the changes can be very different regarding the regime of dispersion that we consider. You can have some temporal compression in the anomalous regime and a large temporal broadening in the other regime of dispersion. But what is the most interesting for us, this is that the prediction of the output provided by the nonlinear Schrödinger equation, here in black, is in very close agreement with the prediction of the neural networks after a convenient training. You see, they are both in excellent agreement. We can add some attenuation or optical gain in our system. It will, for example, enable you to generate this nice parabola at the output of the system. And here, the same conclusion holds. Prediction by nonlinear Schrödinger equations are in close agreement with predictions of the neural network. And this is true on several decades here, as we can see in the temporal domain. And now, if we change the input shape of your pulse, new dynamics become available, such as spectral compression or the generation of a flattened pulse. But it does not change the conclusion here. NLSC and neural network are still very close. So with this different example, we can see that even a simple structure of neural networks can reproduce completely the results of the nonlinear Schrödinger equations after a proper training. Let's now discuss another case. Here, instead of a pulse, what we will use at the input, it is a signal made of three different frequencies that are equally spaced, and we can characterize this input signal by two parameters. So eta is the ratio between the energy in the central component and the total energy of the system. And phi is the relative phase between the various spectral components. After propagation, as there is dispersion and Kern nonlinearity, there will be a change in the energy of the different spectral lines. So eta will change, and there will be also a change in the relative phase. You can model it by rewriting the nonlinear Schrödinger equation into three coupled equations. And if you do some further physics, you can find an Hamiltonian for this system. And what is interesting, this is that the canonical variables of this Hamiltonian are the eta and phi parameter that I have described. And you can then characterize the dynamics of your system using these differential coupled equations. And if you plot the result on phase plot, what you see, this is some nice close orbit with behavior that may differ whether you are on the right or left side of a separatrix. So to confirm all that, we have built a dedicated experimental setup that enables us to record the changes over a short distance of propagation, typically half a kilometer. So we have this kind of data with changes over a short length of propagation. And with such data, we can train a neural network. So once again, a configuration that is very simple with only 12 neurons that are involved. And from this simple neural network, we are then able to retrieve the full dynamics of the experimental setup. And we can say that we observe some close orbits that are different according to the side with respect to separatrix. And as we have both the intensity and phase information regarding the system, we can rebuild also the temporal evolution of the waves. And what we see, this is that what we reconstruct from the neural network is in close agreement with the nonlinear Schrödinger equation predictions. So from experimental results, we are able, thanks to the neural network, to accurately predict the dynamics over tens and tens of kilometers. Now, if we want to take into account the cascaded generation of new sidebands that ultimately may lead to the generation of a comb, we need to have a neural network with a bit more neurons that have taken into account. And in the end, what we have, this is again the same conclusion. This is that the neural network is able to retrieve the dynamics that happened in the generation of this comb, both in the anomalous regime of dispersion as well as the normal regime and dispersion. And the agreement is very nice, both in the temporal and spectral domain. We have a very high accuracy. In the three previous examples, I have mainly focused on the use of feed-forward neural network, but as I have already said, there are many other architectures that exist, and there are, for example, recurrent networks or convolutional networks that have been at the basis of the revolution of deep learning. In those cases, the internal structure of the neural networks can be a bit more complex with, for example, some memory that may come into play. So here, those are architectures that you can test. They can be more powerful. They can require, for example, less sample for the training. There is also another direction that is for me quite interesting. This is the possibility to include some physical constraint during the training of the network through a loss function that will include those constraints. So that lead to physics-informed neural networks that can be quite interesting when you investigate some physical process. What happens if now, instead of just a phenomena that is governed by the nonlinear Schrödinger equation, you need to include higher order terms, such as it is required when you consider, for example, the generation of a supercontinuum? Well, the main consequences will be that it will change your data set that you use for training. But in principle, it does not change the concept of using an artificial neural network. Perhaps you will have to tune your hyperparameters. Perhaps you will have to go for a better efficient internal structure. But all the principle still the same. And the agreement that you can reach remains very impressive, as you can see in that example. And with the power of neural networks, it also becomes possible to investigate some rogue event, for example, to derive from the knowledge of an optical spectrum the intensity of the highest peak power that you may have in your field. Neural networks have also been found relevant for the analysis of coherence when non-trivial wave mixing may happen. And so when you will consider lasers, cavity resonators, of course, the physical model becomes different. You will use other equations to describe the physics, but in terms of handling your neural networks, it will mainly translate into a new set of data that you will use for your training, and it will work, at least conceptually, you will be able to find a very good agreement. So now that I think you are convinced that machine learning can be extremely interesting to make prediction of the behavior of the system, let me describe how neural networks can also be useful if you want to think in terms of inverse design. Sorry. The idea here, this is that you know that physically there is an intensity profile given spectra that you obtain at the end of the system at your output, and you want to retrieve your input properties. So you know the output that is physically generated. You want to retrieve the parameters, the propagations. What you have, this is your data set. Previously, we defined an artificial neural network that links your parameters of propagations to your output of the fiber. Now, we will train a new neural network using the same dataset, but this time, what we will use, this is the output of your system. And from this output, we want the artificial neural network to retrieve the parameters of the propagation. So what we just need to do, this is to switch the input and output. So that sounds very simple. Does it work in practice? Here I have taken the same problems as the one I described before. So we know the intensity both in the temporal and spectral domains, and we want to retrieve the propagation parameters. And the result is that it works. It works very well. We have very nice accuracy in findings the parameters of our propagations. So the neural networks, after the proper training, is able to efficiently retrieve the input conditions. So this is something that is interesting, this ability to make a backpropagation, something that is not physically feasible using the nonlinear Schrödinger equations and the split-step Fourier method. Now, let us see another approach where this time we don't have the exact knowledge of the output of your system. We just have a kind of target. So what we know this is that at the output, we want to obtain a pulse that is close from a target, but we are not sure we are not 100% sure that this target does exactly exist physically. In that context, the previous method with the second artificial networks may not behave so well, at least if you use a feed-forward, fully connected neural networks. There is another strategy that still use this kind of neural networks. And the idea, this is, once again, you take your same initial data set for trainings of the neural network, and then you will benefit from the incredible speed of a neural network. The speed of a neural network has been one of the properties that has really stimulated the development of this area. You can ask the neural network to predict millions of output within a few minutes. So compared to the usual way to handle the problem that will require you to solve the nonlinear Schrodinger equation using the split-step Fourier method, your speed is now improved by several orders of magnitude. So with such a speed, you can use a brute force approach where you will send to the neural networks thousands, millions of initial conditions, and you will ask him for the prediction that you may have at the output. And in all this output, you will then select, thanks to a cost function, the output property that are the closest to your target. So you will have then the corresponding input property. So here, what you have, this is an efficient way to cover your full space of parameter. And with that, you can visualize in which region of your parameter space it could be relevant to search. So here it was an example where we were looking to the generation of Chapri parabolic pulse with a very precise output duration. Here we were trying to have a look at the parameter that leads to the self-similar propagation within an amplifier. So what is nice, this is that we visualize the interesting region in those graphs. And in this example, the goal, it was to generate a combo of a few sidebands with sidebands that are of equal amplitude. And you see, we can easily visualize the regions of the parameters that leads to a flat comb at the output of propagation. And in this last example that also deals with comb generation, we wanted to explore whether it was possible or not to have a kind of inverse four-wave mixing. So we started with three spectral sideband with the same amplitude, and we wanted to know whether it was possible or not to refocus the energy of these sidebands toward the central sideband. And the answer is yes. There is a narrow region of parameters that enable such inverse four-wave mixing, and the phase difference between the sidebands is typically pi over 2, so it will guide some further development regarding some analytical treatment of this process. Is it possible to gain some deeper knowledge of physics using machine learning? So we will see here with three examples that it is possible to extract from data some models or some way to interpret the result. So once again, the nonlinear Schrodinger equation here it's in normalized form. And you have seen before that according to the regime of dispersion, according to the ratio between nonlinearity and dispersion, you can generate at the output very different temporal intensity profiles. Our question was, is it possible to make cluster of those intensity profiles to classify them automatically without having to manually label them? So to test this idea, we have tried a K-means algorithm, which is one of the best known algorithm of clustering. It is an easy algorithm that is already widely available. So it gives cluster. And then we wanted to check whether or not we can give to those clusters a clear physical meaning. So are they the cluster that we may intuitively think when we know the dynamics in a nonlinear waveguide? So here are the results. What you can see is this is that according to the regime of dispersion, the clusters are very different. If I discuss what happens in normal dispersion, you see that the clusters are quite well isolated. The first cluster in blue, this is the region of parameter that do not lead to a significant change in the temporal intensity profile. In purple, the temporal intensity profile begins to change. This is a region where your pulse is experiencing a process that is called wave breaking. And there is an approximate analytical limit that has been found 20 years ago. This is a line here plot in black, and you see that this line agrees well with the border of the cluster that we have. Finally, for normal dispersion, there is a cluster in red that is linked to a spectronic regime where your pulse does not change in shape, but experience a temporal broadening that you have its temporal duration that continuously increases. The cluster in the anomalous regime of dispersion is a bit more complex. You have part where your pulse does not change, but you see that there are blue clusters that are within the other clusters. And this process, this is linked to the recurrence phenomena that may appear when you consider a higher order soliton, for example. You have clusters in yellow that correspond to the stage where the pulse experience some temporal compression, and the line in dashed is an analytical formula for the point of maximal compression. And finally, the last cluster in green is associated to pulse splitting. So from the different clusters on the K-mean algorithm, it's also possible to define a typical profile of this cluster. This is the centroid, and you see that this typical cluster confirm our analysis. So without any labeling, it is possible to directly classify the temporal behavior of the pulse upon propagations, and this automatic clustering is fully understandable in terms of physics. Now, a bit more complex problems. This is a propagation of a continuous wave within an anomalous fiber. And in that case, the continuous wave breaks into multiple pulses, then experience some stages of growth and then decay. So here we wanted to identify which are the dominant effects that governs these dynamics. And to answer this question, we use an algorithm that is called the dominant balance model that has been proposed by Kunz and Burton. And from this, we can identify that in the part plot in blue, this is a Kerr nonlinearity that dominates. So here, the strength of this approach is that it provides you an information not only at the different distance of propagations, but also at different times. In the part plot in orange, this is typically the part where you see structures that grows and decay. It is essential to both include dispersion and nonlinearity. So here you get clues from the method to interpret your nonlinear dynamics. So this work has been made at the University of Bourgogne Franche-Comté. Now, another example, this is when you consider the propagation of a pulse in a normally dispersive fiber. You have, this time, different effects that will impact your pulse according to the distance of propagation. So in the central part of your pulse, it will be the Kerr nonlinearity that will dominate both in the temporal as well as in the spectral domains. If now you consider only the wings of your pulse or spectrum, it will be mainly driven by dispersions. And between the two, you have to take into account both effects. So you see that we have here really a powerful tool to analyze the dynamics, and this tool can be also extended to include higher order terms such as third order dispersion or Raman scattering. To finish with these tools to retrieve some additional physics from data, let me go back to the problems I've previously described, where you consider three spectral lines that will be affected by dispersion and nonlinearity upon propagation. So as we have seen, it leads to a trajectory characterized by close orbit when you consider eta and phi as the parameter of your propagation. And here, what we wanted to know, this is whether it is possible or not to retrieve from this orbit the governing equations of the process. So the answer is yes, and we use here result once again from Burton and Coase. I strongly encouraging you to go to their YouTube channel, where there are plenty of very interesting and very pedagogical resources. And the algorithm they've proposed is known as the space identification of nonlinear dynamics, SINDAI. And we start from the knowledge of several trajectory, where we have a sequence of eta and phi. And the first step of this algorithm, this is to derive the derivative of those trajectory. And then we will try to link the trajectory with the derivative. And to make this link, we will propose various functions. So we will create a library of potential function that can be polynomial term, that can be periodic function, or it can be a combination of polynomial and periodic terms. And the algorithm SINDAI will identify for you the most relevant terms, and it will also provide the coefficient that you will need to include. And if we compare the known equation with the output of the SINDAI parameter, well, the results are quite stunning. The terms to be involved are conveniently identified, and the coefficients are also completely retrieved. So here were the results using noise-free data, but it has been shown also that it can be extended, and it works when you also include some noise to your analysis. And such a technique can be useful to investigate, for example, also behavior of structures within fiber lasers. So now, in the last part, I will describe the use of machine learning for smart lasers. Lasers, fiber lasers have many advantages, but sometimes they still suffer from one drawback. This is that you need to tune some parameters empirically, manually. For example, have a state of polarization in a fiber laser where this is a nonlinear polarization rotation, that is the mode locking process. The idea, so it was to replace this manual adjustment by the use of some artificial intelligence, and it works. So it is possible to have a laser mode lock automatically at the fundamental repetition rate, so the same pulse that repeats every one trip. And it is also possible to reach, for example, higher mode locking, higher order mode locking, where you have 2 pulses per round trip, 3 pulses per round trip. Most of these smart lasers are based on evolutionary algorithm, and one of the main evolutionary algorithm, this is a genetic algorithm. So what you need, this is a measure of your behavior of your lasers, and you also need to be able to tune your parameters of your lasers in a controlled way, so to apply here a deterministic feedback. And the optimization algorithm, your genetic algorithm, will link your measurement to your feedback. And how does it work? Well, configuration of your laser, it is an individual. And each parameter that you can change is a gene of your individual. And you start your study by considering a set of various configuration of your laser, so a population made of several individuals. For each of your individual, you measure the performances of your lasers that you will compare to your target through a fitness or a target function, and it will tell you if your result is satisfying or not. If you have met your target, then everything is perfect. But if it is not the case, you will select in your population only the best individuals. You will make some crossover between the genes of various individuals, and you will also apply some mutation by changing slightly parameters of your gene. And all that will bring you a new populations that you will apply through your feedback to your lasers, and then you reiterate until your fitness function is met. So we have tried to apply those genetic algorithm to an operation regime of fiber laser that is different to the usual mode locking, where the pulse is identical from one trip to the other. In the pulsating or breathing operating mode, your pulse experiences some changing in its temporal and spectral properties from one road trip to the other. Can be also changes in its energy. You can generate also pairs of such breathing pulses or even molecules. So we wanted to implement all that. So this is work that has been done at East China Normal University with lasers that use nonlinear polarization rotation as a mode locking process. What is important, I say it again, this is all the diagnostic tools that you will have and the control that you may have on your mode locking process. Each degree of freedom that you will have will be one gene for your genetic algorithm. So you bridge your result of diagnostic with your feedback by the evolutionary algorithm. And you need to find the good criteria or combination of good criteria. In our case, it was the optimization of a small sideband that you can find in the vicinity of the radio frequency peak that is typical of the repetition rate. So if we can play with this small peak, then we will get an accurate control on the breathing property, and it works. It works very well. It is possible to change the breathing ratio or the breathing period, and we can have control to generate triplets or quadruplets of pulse. So here, very powerful techniques that is also able to handle non-stationary phenomena such as the generation of extreme event within a fiber. So using genetic algorithm, it was possible to generate some super rock wave at the output of the fiber lasers and to have control on those super rock wave. It was also being used to optimize the bandwidth at the output of a laser that operate in the noise-like regime. The difficulty this is that the region of parameters that lead to optimal operation is very tiny, is very narrow region of parameters, but the genetic algorithm is good at finding it. The power of this genetic algorithm can be also used to optimize the profile of a supercontinuum, for example, to get most of the energy of the supercontinuum at a given wavelength. Here, it has been done through the spectral phase shaping of a pulse before it's launched in a highly nonlinear fiber. And it can be also done on a chip using a control sequence that is obtained through the use of various interferometers. So it is now time for me to conclude. So I hope that I have managed to convince you that machine learning can bring you some new tools that are extremely powerful. It can be extremely interesting both from the theoreticals as well as the experimental side. It can help you to identify the most relevant region of parameters. It can help you also to find some physical insight. There are many approaches that are possible. Of course, there are some approaches that are quite complex, but some other are rather simple, and you do not need to be an expert in computing science to implement those tools. So we have here something new that now you need to have in your toolbox. I think we are just at the beginning of this use of machine learning, and there are still many things to be investigated. And just to finish, I have focused on the use of machine learning to improve photonics when you deal with waveguide and nonlinear propagation, but you can also use nonlinear photonics in a fiber to improve machine learning. And this is what is explored in the context of X-trend learning machine, with here 3 different examples that may use nonlinear multimode fiber, supercontinuum generation, or frequency comp. So thank you for your attention.